Okay, this is another circular motion problem. So in here we're thinking about an amusement park ride, and it's called the Rotor because it's a big circle that spins around. So it's one of these big circles, and it spins around, and after it reaches a certain high speed, the floor is removed, and so the people feel like they're getting crushed up against the wall, and that's why they don't slide down. And so what we want to analyze is why that really happens. So to start this problem, one thing we have to do is think about what are the convenient points to consider. So I'm going to take 4 points, one on each side of the circle, and I'm going to consider what's going on at each of those points. So let me label them 1, 2, 3, 4. Okay, and I'm going to start at 1. So if I draw a free body diagram for a person who's on this ride at point 1, what I have is force of gravity that is pointing down. Trying to think about orientations here. Right, so the force of gravity is pushing down, and what I know is happening is that the rotor must also be pushing. The ride itself must also be pushing to the center here. But the question is, what's pushing up? If the ride is pushing in towards the center of the circle, what's resisting gravity? So there must be some frictional force here that's resisting the pull of gravity. And so in this case, the centripetal force is the force normal at point 1. Okay, so that's a free body diagram for point 1. Let's do the same thing for point 2. At point 2, what we have happening is the force gravity is still pointing down. The normal force is still the thing that's pushing in, and the force of friction is still the thing that's pushing up. So what we can sort of see here is because this rotor is always oriented where the people are getting pulled down by gravity, that the centripetal force is always the normal force, and the force of friction is always the force that's pushing up against gravity. So if we wanted to figure out then what speed, let's say for instance, the rotor needs to move in order for the average person to not fall, what we'll use here is that the sum of the forces and the y have to be equal to 0 for the people to stay constant, and the sum of the forces and the x must be the centripetal force. So Fc, which must equal mv squared over r, right? Okay, so we'll call y, we'll call x. So sum of forces in the y, then we've got the force of friction minus the force of gravity has to equal 0. So the force of friction has to equal the force of gravity. We know the force of friction here is mu force normal, force of gravity. But from this expression, we also know from the x direction, we also know that the force normal has to equal mv squared over r. Right, so we can use this guy and this expression. So we can use mu mv squared over r equals mg, so that the m's cancel out. And so we can solve here for v. We find that it's gr over mu. Now here's a question, which mu should we be using here? And we get both of them, both the static and the kinetic. So which one should we be using? Well, if we think about it, what we want is the people to be sitting still on the wall and not moving up or down. So the coefficient of friction we want to use here is the static coefficient. And so we find then that the v squared is equal to 9.81 meters per second squared. So r should be the radius of the amusement park ride, which we are told it's 4 meters. And then the mu here we want to use is 0.6. I know that's the static one because it's bigger, and I know that the kinetic friction must be less than or equal to the coefficient of static friction. So then I plug that into my calculator, and I get that the velocity that this thing has to be moving at is 8.08 meters per second. Okay, now one thing to know is that this ride, this was simple because this ride was moving always parallel to the ground. But if we were to flip this and have it be a loop-de-loop of a roller coaster, it would look slightly different because the forces that are acting on each point of that circle would be different forces than the rotor amusement park ride.